Hello guys, and welcome to our YouTube channel IQI Science. As you know, in our randomly released videos, we discuss various topics related to technology and scientific areas such as space, astronomy, physics, engineering, chemistry, computer science, artificial intelligence, future innovations, and gaming. So I'll request you all to stay tuned and subscribe to our channel and keep supporting us. Today we will discuss about a very interesting topic which is called deep learning or artificial neural network. So what is deep learning? So deep learning is a type of machine learning. As here you can see, the artificial intelligence is a very broad topic, and within this topic machine learning is a subset, and within machine learning deep learning is a subset. So deep learning is a type of machine learning techniques in which a model learns to perform classification tasks directly from images, text, or sound. Deep learning is usually implemented using a neural network, as you all know. So deep learning is usually implemented using a neural network architecture. The term deep refers to the number of layers in the network. The more layers you have, the deeper the network. Traditional neural networks contain only 2 or 3 layers, while deep neural networks can have hundreds of layers. Deep learning is especially well suited to identification applications such as face recognition, text translation, voice recognition, and advanced driver assistance systems, including lane classification and traffic sign recognition. Advanced tools and techniques have dramatically improved deep learning over the years. As you can see here, that before 2012 we had more errors, but over the years, as you can see, that after 2012 the newest structures got improved a lot, and the accuracy has been improved, and it has come to a level where it can perform as good as human. So, and it will improve, continue to improve. So you know that advanced tools and techniques have dramatically improved deep learning algorithms to the point where they can outperform humans at classifying games, classifying images, win against the world's best Go player, or enable a voice controlled assistant like Amazon Echo and Google Home to find and download that new song you like. So that's pretty much about deep learning. Let's see the difference between machine learning and deep learning. So what is machine learning? Machine learning actually is a subset of artificial intelligence where you manually extract relevant features from an image, and it performs well if the data set is small, and the benefit is it takes less time and it is easy to train a model, whereas deep learning is a subtype of machine learning, and deep learning requires very large data set. Computationally it is intensive, and deep learning learns the features automatically from the images you provide, and the accuracy can be greatly enhanced. And as you know, over the years the GPUs got really powerful, and so the and that is for that recent deep learning models are performing a lot better than previous models due to this computational power. Okay, so let's dive into artificial neural network. So what are they? So an artificial neural network, ANN, is a mathematical model, as you can see here, it is the basic form of a neural network, which is called a neuron. It is the I will be telling you about the classical, most basic form of neural network here. So an artificial neural network is a mathematical model that is inspired by the structure and functional aspects of a biological neural networks. It consists of an interconnected group of artificial neurons here, as you can see. So it consists of an interconnected group of artificial neurons, which is programming constructs that mimic the properties of a biological neuron, as you can see here. And it processes information using a connectionist approach to computation. In most cases, an ANN is an adaptive system that changes its structure based on external or internal information that flows through the network during the learning phase. As you can see here, they are usually used to model complex relationships between inputs and outputs, or to find patterns in data. Artificial neural networks are computing systems that are inspired by, but not necessarily identical to, the biological neural network. The biological neural network, or you can call it neuron. Such systems learn to perform tasks considering examples, generally without being programmed with any task specific rules. For example, in image recognition, here you can see, in image recognition problems, they might learn to identify images that contain cats by analyzing example images that have been manually labeled as cat or no cat, just like here, and using the results to identify cats in other images. As you can see, finally the neural network has learned to differentiate between cat and dog, because initially you provided label data where it was identified as cat. They do this without any prior knowledge. The artificial neural networks do this without any prior knowledge about cats. For example, we know that they have fur, tails, whiskers, and cat-like faces. Instead, they automatically generate identifying characteristics from the learning material that they process. An ANN is based on a collection of connected units. As you can see here, it is based on a collection of connected units, or we call them nodes. So these nodes are called artificial neurons, which loosely model the neurons in a biological brain, like this one. Each connection, like the synapses in a biological brain, can transmit a signal from one artificial neuron to the other one. So The biological neurons are also called BNN, biological neural network. So each artificial neural is computed by some nonlinear. So here you can see that each connection, like the synapse in a biological brain, can transmit a signal from one artificial neuron to another. An artificial neuron that receives a signal can process it and then signal additional artificial neurons connected to it. In common ANN implementation, the signal at a connection between artificial neurons is a real number, and the output of each artificial neuron is computed by some nonlinear function of the sum of its input. As you can see here, the connection between artificial neurons are called edges. And artificial neurons and edges typically have a weight, like this one, typically have a weight that adjusts it as learning proceeds. The weight increases and decreases the strength of the signal at a connection. Artificial neurons may have a threshold such that the signal is only sent if the aggregate signal crosses that threshold. Typically, the artificial neurons are aggregated into layers, just like this one. So, different layers may perform different kinds of transformations on their input. An artificial neural network is a network of simple elements called artificial neurons. So, artificial neurons which receive input change their internal state. It's also called activation according to that input, and produce output depending on the input and activation. The biological neural networks are made up of real biological neurons that are connected or functionally related in the peripheral nervous system or the central nervous system. The fundamental processing element of a neural network is a neuron. Basically, a biological neuron receives input. Here is the input, as you can see, the dendrites. Basically, a biological neuron receives inputs from other sources, combines them in some way, and performs a generally nonlinear operation on the result, and then outputs the final. So here the synapses are connected to another neuron. As you can see, the dendrites accepts inputs, and the soma process the out inputs, and axon sum the processed inputs into outputs, and synapses are the electrochemical contact between neurons. So this network is mimicking this actual biological neuron in some way. These components are by their biological names: dendrite, soma, axon, and synapses. Artificial neural networks may either be used to gain an understanding of biological neural networks or for solving artificial intelligence problems without necessarily creating a model of a real biological system. The real biological nervous system is, although highly complex, artificial neural network algorithms attempt to abstract this complexity and focus on what may hypothetically matter most from an information processing point of view: good performance, that is, as measured by good predictive ability and low generalization error. So how the training happens in artificial neural network, let's see that. So training: once a network has been structured for a particular application, that network is ready to be trained. To start this process, the initial weights are chosen randomly. Here you can see these are the weights and these are the inputs. So then the training or learning begins. There are two approaches to training. One is supervised learning and the other is unsupervised learning. Supervised training. So what is the supervised training? Supervised training involves a mechanism of providing the network with the desired output either by manually grading the network's performance or by providing the desired outputs with the inputs. And the unsupervised training is where the network has to make sense of the inputs without an outside help. So in supervised learning, both the inputs and the outputs are provided. So both the inputs and the outputs are provided. Then the network processes the inputs and compares its resulting outputs against the desired outputs. Errors are then propagated back through the system, causing the system to adjust the weights which control the network. With supervised learning, the artificial neural network must be trained before it becomes useful. Training consists of presenting input and output data to the network. This data is often referred to as the training set. Here you can see the training set. So this is called the training set. That is, for each input set provided to the system, the corresponding desired output set is provided as well. In most applications, actual data must be used. This training phase can consume a lot of time. In prototype systems with adequate processing power, learning can take weeks. The training is considered complete when the neural network reaches an user-defined performance level. This level signifies that the network has achieved the desired statistical accuracy as it produces the required output for a given sequence of inputs. When no further learning is necessary, the weights are typically frozen for the application. So the weights are typically frozen for the application. Some networks type allow continual training at a much slower rate. While in operation, this helps a network to adapt to gradually changing conditions. Training sets need to be fairly large to contain all the needed information if the network is to learn the features and relationships that are important. Not only do the sets have to be large, but the training session must include a wide variety of data. After a supervised network performs well on the training data, then it is important to see what it can do with data it has not seen before. This is called validation. If a system does not give reasonable outputs for this test set, the training period is not over. Indeed, this testing is critical to ensure that the network has not simply memorized a given set of data, but has learned the general patterns involved within an application. So, what are the other components of a artificial neural network? These are called the inputs, and these are called the weights. Weights are typically a neural usually receives many simultaneous inputs, as you can see x1 to xn. So each input has its own relative weight, which gives the input the impact it needs on the processing element's summation function. In both cases, some inputs are made more important than others, so that they have a greater effect on the processing element as they combine to produce a response. Weights are adaptive coefficients So these are adaptive coefficients within the network that determine the intensity of the input signal as registered by the artificial neuron. They are a measure of an input's connection strength. These strength can be modified in response to various training sets and according to a network's specific topology or through its learning rules. And the next is the summation. So what is summation? The first step in a processing elements operation is to compute the weighted sum of all the inputs. The summation function can be more complex than just simple input and weight sum of products. Just like this one, this is the weight sum of products. The input and weighting coefficients can be combined in many different ways before passing on to the transfer function. So it goes through a transfer function. Some summation functions have an additional process applied to the result before it is passed on to the transfer function. This process is sometimes called the activation function. 5. The purpose of utilizing an activation function is to allow the summation output to vary with respect to time. So what is a transfer function? The output of the summing, here you can see the output of the summing just like this. The output of the summing function is then sent to a transfer function, and this function then turns this number into a real output via some algorithm. So via some algorithm that as you know, it is this algorithm that takes the input and turns it into a 0 or a 1, a -1 or a 1 or some other number. The transfer functions that are commonly supported are sigmoid, since sine function, or hyperbolic tangent functions like this one. As you can see, this is the weighted average of the input and the weights. So this goes to the transfer function, and here is an example of a nonlinear transfer function where you can see the result of the summation function, almost always the weighted sum, is transformed into a working output through an algorithmic process known as the transfer function. It is in the transfer function, the summation total can be compared with some threshold to determine the output. If the sum is greater than the threshold value, the processing elements generates a signal. If the sum of the input and weight products is less than the threshold, no signal or some inhibitory signal is generated. Both types of response are significant. The threshold or transfer function is generally nonlinear like this one, as you can see here. The nonlinear functions are used because linear or straight line functions are limited because the output is simply proportional to the input. Linear functions are not very useful. This transfer function also can scale the output or control its value via a threshold. The result of the transfer function is usually the direct output of the processing element. So what is scaling and limiting? After the processing element's transfer function, the result can pass through additional processes which scale and limit. This scaling simply multiplies a scale factor times the transfer value and then adds an offset. Limiting is the mechanism which ensures that the scaled result does not exceed an upper or lower bound. This limiting is in addition to the hard limits that the original transfer function may have performed. And after that it becomes we get the output function. In output function, each processing element is allowed one output signal which it may output to hundreds of other neurons. So this will go to the next neuron. This is just like the biological neuron, where there are many inputs and only one output action. Normally the output is directly equivalent to the transfer function's result. Some networks topologies, however, modify the transfer result to incorporate competition among neighboring processing elements. Neurons are allowed to compete with each other, inhibiting processing elements unless they have great strength. Competition can occur at one or both of two levels. First, competition determines which artificial neuron will be active. So, first, competition determines which artificial neuron will be active or provides an output. Second, competitive inputs help determine which processing element will participate in the learning or adaptation process. Next is the important part, which is error function and backpropagated value. In most learning networks, the difference between the current output and the desired output is calculated. So this raw error is then transformed by the error function. To match a particular network architecture. The most basic architecture use this error directly, but some square the error while retaining its sign. Some cube the error. Other paradigms mostly modify the raw error to fit their specific purposes. The artificial neurons error is then typically propagated into the learning function or another processing element. This error term is sometimes called the current error. The current error is typically propagated backwards to a previous layer, yet this backpropagated value can be either the current error scaled in some manner, often by the derivative of the transfer function, or some other desired output depending on the network type. Normally this backpropagated value, after being scaled by the learning function, is multiplied against each of the incoming connection weights to modify them before the next learning cycle. So what is learning function? The purpose of the learning function is to modify the variable connection weights on the inputs of each processing element according to some neural based algorithm. This process of changing the weights of the input connections to achieve some desired result can also be called the adaptation function as well as the learning mode. There are two types of learning. I talked about it a moment ago: supervised and unsupervised. Supervised learning requires a teacher. The teacher may be a training set of data or an observer who grades the performance of the network results. Either way, having a teacher is learning by reinforcement. Then there is no external teacher. The system must organize itself by some internal criteria designed into the network. This is learning by doing. So here you can see there are artificial neural networks are divided into feed forward and feedback. There are a lot of architecture types. Mostly the feed forward networks are two types. One is linear and the other one is non-linear. The linear ones are not that useful, and the non-linear is divided into unsupervised and supervised network. And there are feedback network, and there are also self-organizing network. So how do we start? How do we create and train a network? So what is the workflow? First, you have to access the prepare your data. There are lots of training dataset available on the internet. These label data. So first you have to access and prepare your data. Then you have to create the neural network using Python or MATLAB. Then next you have to configure the network's input and outputs, tune the network parameters, the weights and biases to optimize the performance. Then you have to train the network and then validate the network's result, and after that integrate the network into a production system like enterprise systems, clusters, clouds, or you can deploy your network to an embedded device. So you can see that there are a lot of different types of artificial neural networks. So here you can see that there are feed-forward neural network. So in feed-forward neural network, this is actually the recurrent neural network. As you can see, the recurrent neural network, in recurrent neural networks, the it propagates data forward but also backwards. So data goes backward and also forward from later preprocessing stages to earlier stages. So there are some types of recurrent neural network, just like Elman network and Jordan recurrent neural network. So here you can see in Jordan recurrent neural network, outputs goes back to the back, and here in Elman network, the hidden from the hidden layer, the it goes back. So there are other types of neural network such as feed-forward neural network. In this network, the information moves only from the input layer directly through any hidden layers to the output layer without cycles. One popular type of feed-forward neural network is convolutional neural network, CNN. Others are like probabilistic neural network. There are more and various structure types of neural networks. Some are like regulatory feedback network, radial basis function network, dynamical neural networks such as neurofuzzy neural network. So that's pretty much it. We saw that learned about a little bit about neural network here. So that's pretty much it. So we will end our session today, and thanks for staying with us, and be sure to subscribe to our channel. So that's it for today. Don't forget to subscribe our channel. Thank you.